Can we use a feature of size as a datum? Yes, we can. And just to review, remember that a feature of size is basically something you can measure with a caliper. Oftentimes, you look at how the part functions, but oftentimes you want the center axis or the center plane of a thing to be the place from which the measurements are taken. And if that's the case, then you use that feature of size as your datum. When you use a round thing as a datum, the datum axis becomes the datum, and it actually establishes a primary and a secondary datum in there just by virtue of being an axis. If you put a datum on a planar feature, a thing made of planes like this notch, like datum C, then the datum is a center plane. When you put these datum identifiers on, if you put them opposite a size dimension, that means it's the feature of size axis or center plane that is the datum. You can also attach them to the hole or the circle, and that means the center axis. And you can attach them to the feature control frame that's part of the feature of size. And then on a flat thing like a notch or a keyway, again, put the symbol directly opposite the dimension arrow, or maybe replacing the dimension arrow, and that means the feature of size, the center plane, is the datum. And you can also attach that box to the feature control frame. So these guys here are not features of size, they are attached to surfaces. So these are talking about surfaces being datums. These guys are talking about center axes being datums. It's a distinction. And these are talking about center planes being datums. Here's an example from ASME that shows some. I'm going to skip over that. And you remember that we have a datum reference frame anytime we set up a primary, secondary, and tertiary datum. They are theoretically 90 degrees apart. Well, when you have an axis, you still have a datum reference frame. It's just that two of those planes are going through the axis. I stuck this in because it's cool. This is an example out of the ASME standard. I colored it in Photoshop. Looks like a generator or something. They're talking about datums. Now, I'm going to buzz through these slides kind of fast. There's an awful lot of detail here. What I want to show you is that here are 6 holes with a position control. So this is controlling the position of those 6 holes. And they say surface A is the primary datum, so there's surface A. Feature B is the secondary datum. There's feature B, it's that hole. And what I want to point out is there's no M in here. And what that means is that must be simulated regardless of feature size. Whatever size you happen to make this hole, you've got to contact the part regardless of feature size. So our inspector has to use, I don't know, a collet or some kind of expandable, adjustable thing. However, if you control the position of these holes and you put an M after datum B, B is still that center hole, but now there's an M. M means fixed gauge. It means your gauge does not have to be adjustable. It is a fixed size. So our inspector is going to figure out, and we'll come to this later, don't worry about this word, virtual condition. Our inspector is going to figure out what is the virtual condition of that hole, and that is the size that they will make that gauge pin. And now when our inspector checks the part, they just drop the hole over that gauge pin onto this flat surface and now take their measurements. You can simulate an axis if you're inspecting a pin You can simulate an axis with a very precise gauge with a hole in it. You can simulate an axis if you're checking a hole by using a precise gauge pin, and it becomes the axis. If you're checking a flat feature, you can use two flat gauge tools that are very precise, that are a certain distance apart, and they simulate the center plane feature. This slide just talks about how it makes a difference which order you put the datums in. I think I will skip over this because it would take some time, but just come back and look at these pictures sometime, and you will notice that the order of the datums makes a difference. I'm going to skip over these two because they're talking about whether or not you have an M. Okay, I'll briefly talk about them. They're talking about whether or not you have an M after your datum reference. So in this position control, feature B, which is the axis of this pin here, feature B will be the primary datum, but there's no M after it. And what that tells us is this datum has to be simulated regardless of feature size, and that means contact the surface. That means we've got to have a collet or a chuck or something adjustable. Blah, 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 blah. However, if we call out our primary datum with an M after it, that means we can simulate the axis of pin B here at maximum material condition. In other words, we can use a fixed size hole in our gauge tool. M tells us fixed gauge. Remember that. Here we are, some more about that. More about that. Like with surface datums, with feature of size datums, whatever your primary datum is, 3 points of contact, usually you have some kind of form control on it. You don't want to just throw a rough and bumpy thing out there. You have some kind of qualifying form tolerance. Finally, I wanted to tell you about something called a compound datum in these last two slides. What if you've got some shaft, like in a, I don't know, a car engine or something, and the ends of the shaft have to fit into, let's say, bearings. There's a bearing on each end. And that's the way the part functions. So when you're inspecting this part, you want to simulate those bearings on each end. So you want a gauging tool, this brown stuff here, that will simulate the part as if there were one continuous datum axis running through it. And how you write that on your drawing is like this. So this symbol on the drawing is called runout. That's where you rotate the part and you put a dial indicator thingy on there and watch the needle go up and down as you rotate the part. This says hold the part with a compound datum, A-B. That means you'll grab end A and you'll grab end B, and those will work together as one datum axis. Neither one is more important than the other. They work together. Here is an example of a compound datum axis. This is not out of our dimensioning and tolerancing standard. This one happens to be out of the castings and forgings standard, but I thought it was interesting that they too are using a compound datum. So here is something like a crankshaft, where each end has to go into one of those pins centered up. so that we can inspect this thing. So they have written A-B. A and B together make a compound datum axis. I realize that was a whirlwind tour. There is a lot to say about feature of size datum axes, but that's just skimming the